Understand hashing?
Delicious.
Wow. Okay. I mean, I heard cool before, but delicious is a new thing. All right. So we're going to cover hashing next time. Now we're going to focus on P set 3 because I heard P set 3 is hard. So we're going to look at the code and try to understand it. I tried to make it easy. I really tried. Okay, so how many people recognize the code? Does this look familiar? 1, 2, 3. Everyone else got stuck on question 1? Okay, so I'm not going to give you the answers to the P set. We're going to look at the code and understand what it does. Because once you understand what it does, you can understand how to modify it. All right, before I do that, any questions? And I might not answer them right away, but I'll keep them in mind while I go through the code. Are there any specific pain points?
Event types.
Okay. Yep. Covered in 5 minutes.
Yeah.
Oh, well. All right, so the first thing that I want to talk about is sweep line algorithms. So we're asking you to implement the sweep line algorithm, and we're giving you one that is horribly inefficient. So suppose you have some line segments that look like this. Sorry, drawing isn't. Okay. So they look like this. And suppose you want to find the intersections between them. Let's figure out what the algorithm that we gave you does. Did people look at the trace for that? So not the good trace, the trace that's output by the algorithm that we gave you. Does anyone understand what that does?
I kind of get it.
Okay.
I think what it does is it just hits through all the horizontal lines.
Okay.
And then it goes through all the vertical lines.
Okay, so first it goes through all the horizontal lines, and what does it do with them? All right, so they get bolded in the visualizer, which means they're added to the range index. So 1, add all the horizontal lines, and 2, oh, you said it goes through all the vertical lines after that. Any idea what it does?
Looks for intersections.
Okay, so when it looks at a vertical line segment, you'll see some blue square and you'll see some segments that are green. This is a query to the range index. And the green segments are the answers, and the blue square is the range that's queried. So first add all the segments to the range index, and then do a query. So in principle, sweep line algorithms have some geometric inputs, for example, a bunch of lines. And conceptually, they have this vertical line that they sweep across the plane all the way from -infinity to +infinity. So now if you try to sweep a line continuously from -infinity to +infinity in code, it might take forever. So we don't really do it that way. The way you do it in code is you know when something interesting is going to happen, and you only simulate what happens to the sweep line at that point. So in this case, the sweep line starts at -infinity. And then all the horizontal segments are added to a range index. And then as the sweep line goes across the plane, when it hits a vertical segment, a query happens. So the only times when the sweep line stops is first at the beginning to add all the horizontal line segments, and then every time it hits a vertical line segment. We know this ahead of time, so we can compute a list of all these coordinates of interesting things, and then we can sort them and then go through them and simulate the behavior of the sweep line that way. So if you look at the code listing at events from layer, this is the gist of it. This is what it does. So it compiles a list of events. The first key in each event is the x. Is that x? Yeah. X like this, y like this. So the first key is the x coordinate of an event, and by sorting that list of events, it will then process them in order. So events from layer is responsible for looking at all the wires and compiling events. How does an event for a horizontal layer look like? Can anyone tell me? sorry, for a horizontal wire.
The leftmost point.
Okay, so first off, it looks like a list, right? It's a regular Python list. And I will try to call it vector so that we don't confuse it with a big list of all the events. So you said the first thing is the leftmost point, right? So if this segment, for example, starts at minus 100, this one starts at minus 95, this one starts at minus 90, and this one starts at minus 50, by the way, not to scale, then the leftmost point is minus 100, right? So this is the first element in the vector. And that's computed on line 4, where it goes through all the segments, looks at all the x coordinates, and chooses the minimum. Okay, what's the next thing in the vector? We don't have to understand why. We'll go through why in a bit. I'm just interested in what?
0.
0. Excellent. All right, after that, there's a wire ID. So each wire gets a unique ID. That's a number between 0 and the number of wires. So say this is 1, 2, 3. This is going to be 1. And then I have the string add. And then I have the actual wire object. All right, what does the vector look like for a query event? So sorry, what does it look like for a vertical wire? Giving away some of the answer. Bad, bad, bad. All right, vertical wire. Look at the code and
Takes the left endpoint.
of the wire, okay. And okay. So a vertical wire will have the same x coordinate for all the points on the wire, right? So I don't really worry about which coordinate it is. This wire is at minus 50, so the first element here is going to be minus 50. What's next?
1.
A 1? Okay. And suppose this is wire ID 4. I'm going to have 4. Query. And the wire. All right, so what happens with these in the init method, which is not shown in the code listing, is after the list is put together, sort is called on it. So these are all compared and then reordered to be sorted according to some ordering relationship. Does anyone know what the ordering relationship is for Python lists? Yeah.
It starts from the first, like the 0, and the next of the list.
Okay.
Sort, and if it's the same as the next one.
Okay, so say if I have 1, 2, 3, and 1, 3, 2. Sorry, and 2, 1, 2. So it's going to look at the first element, and if they're different, then the one with the smaller element is smaller. So 1, 2, 3 as a vector, sorry, as a list, is smaller than 2, 1, 2 as a list. If this guy becomes 1, then they're equal. So then it has to go to the next element, compare them, and see if they're different, we have an answer. If not, we have to keep going all the way until the end of the list. So this is called lexicographic comparison, and this is the same ordering that you have for the words in a dictionary. Right? If you think of each letter as an element in a list, and the word is the list, then this is how you look up words in a dictionary. Okay, so the reason events look like this is so that sort would output them in the right order for the next stage. So, yes?
So does that mean all horizontal wires you're pretending that they start at the same place even though they don't?
Yep, so all the horizontal wires will be sorted, so all these add events will be sorted before the query events. Yep, very good observation. This is what I'm trying to achieve. That's why I have this special value here. I go through some extra effort to compute it. I had to write an extra line of code, so this is the motivation for it. All right, so the first key in the vector is the x element on the sweep line. I could have also had a very large negative value, something that would behave like minus infinity here, and that would work just as well. By computing the left edge, I don't have to deal with that. I don't have to worry of whether my negative infinity is small enough, because if it's not, I will fail the test, and that's bad. So this is the x-coordinate at which the sweep line stops and something happens. So if all the events are at different x-coordinates, then I have my ordering. I'm done. Now what if I have two events at the same time? For example, what if I have two vertical wires? The x-coordinates are going to be the same, so I need to use something else to break the ties, right? The first thing that I use to break the ties is all add events have a 0 here, and all the query events have a 1. And the point of that is, if I have two events at the same x-coordinate, if I have a query and an add, I want the add to happen before the query. So if this is the same, this is going to be different for add versus query. So does that make sense? This is how we order events relatively to each other on the same line. Now suppose I have these two wires. They're both vertical, so they're both going to be queries. They're both at the same index, so I need something else. And that other thing that I have is the wire ID, which is guaranteed to be unique. So I know for sure the comparison will stop here. And the comparison had better stop here, because if the comparison gets all the way to here, wires aren't comparable, so the code is going to crash. So it stops here because the IDs are unique. Everyone is happy. All right, do the events make more sense now? Okay, to complete the picture, if you look at compute crossings, lines 9 and 10, line 9 goes through the goes through the list of events that have been sorted and processes them in order. So sort had better do the right job. And then it extracts the x-coordinate that's here. It extracts the event type that's here. And then it extracts the wire from here. So these guys really are just there to help with the sorting. They're never read afterwards.
Wait, where are the events actually sorted? I thought they're just put in the order.
So the events are sorted in an init method that's not here. It's in the preset code, but it's not here.
Okay.
And that may be a hint that you don't want to change it. As in, you don't need to. So, all right, events look like this. Any questions about events? Everything makes sense? So presumably when you write your own sweep line algorithm, you're going to come up with your own events, which are going to be different. So you're going to change this method to add your own events to the list. And then it's going to be sorted for you, and then you're going to change compute crossings to process your events in the way that they should be processed. Okay, let's look at the range index. What do we store in a range index? Okay, horizontal wires. Very good. What's the point of storing horizontal wires in an index?
So that when you want to query, you can compare it if there's a line with
Okay, so for the algorithm that we gave you, how does a query look like? Suppose I have this wire here, and I'm doing a query for it.
Oh, it just asks to like relist the horizontal wires that are between that Y.
So between this guy's top and this
Yeah.
guy's bottom, right?
Yeah.
So a query would look like this. Yeah. Basically, all the wires that have all the horizontal wires that have their y coordinate between this guy and this guy. Now, if I have a wire that's way up here or way down here, I know for sure that it's not going to intersect this wire, right? So I don't care about it. So the range index helps me eliminate some wires. Now, will the range index eliminate all the wires that don't intersect with this wire? No, okay. Why not?
Well, in this code, it doesn't.
Okay. Yeah, in this code it doesn't. So we're only talking about this code. I'm not talking about the solution code that you guys have to implement.
Oh, it doesn't.
Okay. So how about what's an example of a query that would give me more wires than, that would give me some wires that don't intersect my wire?
Oh, like if they're
So-
in between the y values, but they're, yeah, but they're not actually
Okay, so you mean,
just, yeah.
right, so
Negative infinity to infinity on the x-axis will give you a bunch of wires, and how many of them will intersect with your vertical wire?
If the end before the vertical wire or the end after the vertical wire, then they don't intersect.
okay. So I understood. So I understood this because it matches what I draw. I didn't understand the minus infinity plus infinity.
Well, if you think about the x-axis on the bottom, if you go from all the way on the left to all the way on the right, you're going to get a whole bunch of wires that are short. That
So one wire that. So you're talking about one wire that's like that, or
if
many?
you're grabbing from your range index.
So the range index. The range index has horizontal wires in it.
Right.
Are
Okay.
you assuming that they're all short?
Yes. Which is not necessarily true, but some of them will be short.
So you're saying a lot of short horizontal. Oh, you mean like this, right?
Yeah.
Okay. So that's what you meant
one
from
intersection and
a ton of non-intersections.
Exactly.
Okay, cool. Thank you. So doing a range query on this can give me a lot of false positives. So that's why after I get them, I have to make sure that they intersect, and I can't just blindly output them. Okay, these are bad false positives. These are bad false positives. Now let's look at how the range index works. Can anyone remind me what the range index does? So it's a data structure, right? And it has some operations. What are the operations for it?
It returns everything between two values in a list.
Okay, so you have a list operation where you give it two values, and it will return everything inside the index in the interval between those two values. Okay. What else can I do?
It can also tell you how many, well, I guess, yeah, it returns those keys and how many there are.
Okay, I have count, and you said that I have some wires in, sorry, I have some things in the index, right? How do I get them in there? So these are queries, I need updates.
Yeah, add and remove.
So for the code that we gave you, what is the running time for each of these operations?
Well, it would be, I think, constant for add and remove.
Okay, so add calls append, right? So that is constant. I will agree there.
Oh, but remove, you have to shift everything.
Yep. So suppose I have. Let's start with an example. Let's have. So say I have these keys in my range index. 5, 8, 11, 13. Suppose they're magically inserted in this order. If I want to remove 2, since this is an array, I have to shift everything to the left.
Yes.
So that's
Order at a time.
okay. How about list and count? So what's the running time for count? How does count work?
count goes through all of the keys.
Okay, so count goes
So
through everything
it has to
and
be order n.
cool. So count goes through all the keys, evaluates the predicate that checks whether they're in the range, and then it adds up 1 to the sum for the right ones. How about list?
Also order n.
Okay, so that's a list comprehension. The code is a bit tricky, but it pretty much does the same thing. It goes through the list and it puts all the keys that are in the interval into a new list. Okay, so now let's look at another version on the next page of a range index that is slightly better. What's the rep invariant for this? How is it different from the first one?
So
Sorted array, very good. So the keys look exactly like this, right? Okay. What is the running time for, let's start with add and remove. What's the running time for add and remove?
N order N.
Okay, why is it order n?
No, order log N.
Why is it order log n?
Because you can, if it's sorted, you can look in the middle. I mean, like, you do a binary search.
Okay, so I can do a binary search in order to find out where I insert something, right? But what if I want to insert 0 in this?
Is it log n plus like order n? Does that make sense? Because you have to shift all of the
Yep.
consequent.
Yeah. So worst case, if I have to insert 0 here, I have to shift everything to the right to make room for it. Right? So your first instinct was good. Order n. And question? No more? Okay, cool. How about remove? Order n. Okay, why is it order n?
You have to shift left everything to the right for your.
Okay, is this what you're going to say too? Or okay. So same reason as before. If I want to remove 2, I still have to move everything to the left. I can find the key that I want to remove very fast, but then shifting things is still order n. Okay, how about count? How does count work?
Give you the same thing, wouldn't it?
Binary search says log in.
Binary search, so it's log n. Okay, so if I look at the count there, it's
Though, like, that's telling me how many keys between.
So it's a simple subtraction to find the number of keys between.
But to find the
Yes,
count
log
of
in,
one
log
key,
in.
you have to.
so count calls binary search twice, and then it does a arithmetic operation. Yes.
We log in because, like, with the count from the range list, that's all then because you have to actually search for it. The binary search, you have 2 login operations, and then you just do some correct.
Yep, thank you. Very good. So this is log n because of good old binary search. How about list? I think you're thinking ahead of list. So how about list?
Because if you could list every single thing in the tree.
Get the values, you might potentially have to iterate through it.
Log N plus the length of the list.
Yeah. I was going to do a nice long analysis, and there's the answer. Log n plus, suppose you return I values from the list, I. So why does this matter? If I have a range query from -infinity to +infinity, I have to create a new list, copy all these keys in, and return them. So that's order n. So I can't just say it's log n. On the other hand, if the answers to my list queries are small, say if they're one element, then it's going to take log n time to do a binary search and then order 1 to produce the list if I have a constant size list. So if I just say order n, I'm selling myself short. It's a lot better if I want to have short queries. Okay, what would be the best possible running time for list? So if I had a magic algorithm that works as fast as possible, would I be able to run in order 1 time? So
No.
super fast magic algorithm, order 1. No, why not?
Because you still have to find L and H in your array.
So suppose I have some other data structure, super magical data structure.
So you can do searches in order 1 time, is what you're saying.
Well, you still have to
But there's
get the
nothing left for
contents
that.
of
Yep.
what you're listing. So it would have to be order n.
Yeah, what were you? Okay, so even if I have a super magical data structure where I can do everything that I want inside in order 1 time, then when I produce the output, I still have to write the output.
Oh, right.
So this thing is going to be omega of I, and I can't possibly do any better than that. So no matter what running time you have for a list, it has to include this I. Unless your running time is order n, in which case I is smaller or equal to n. Okay, does this look right to you? So there is a small bug in this code. What if I do count of 4, 11? So binary search returns, if there's a key there, it will give me the position of that key. And if there's no key, it will tell me where I should insert the key, if the key doesn't exist in the array. So if this is my array, then the positions are 0, 1, 2, 3, 4, 5. So count of 411 would do a binary search of 11 and see 4, and then it would do a binary search for 4 and return 2, right? Because if I want to insert 4, I would have to put it here and then shift everything to the right. And 4 minus 2 is 2, therefore it's broken.
Off by 1 block.
Off by 1 block, right? Well, the interesting thing about it is that I had this code. We actually shipped this code between Saturday morning and Sunday evening, and it passed all the tests. So as we go to the next section, keep in mind that this is broken, but it would still pass the test for our problem. And we'll see why in a bit. So count of 411.
So it finds 11 and it says that will return 5, right? For
4.
the run.
Oh.
So binary search, if it finds the key, it returns the position of the key.
Okay, so it will return 4, the line of blocks.
Okay.
And for 4, will it return 2?
Yep, because it tells me where to insert it.
Okay. Then it says 3 elements, or will it count?
Well, it says 4 minus 2, right? The last line is high index minus low index.
Oh, and that's wrong. It should be
Yep.
So are you saying that it tells you where to insert it as opposed to actually inserting it?
Yeah, so binary search doesn't insert the element.
Okay.
It just tells me this is where you'd put it. And then if you look at add inserts it right there. So that's why binary search is done that way, so that would work.
Can I just ask a style question?
Sure.
The underscore before binary search, is that like saying private?
Yep.
Okay.
Wait, what is private?
So private means that it's not part of the public interface of the class. So if I give you, like if we're in a team and we're working on something, if I mark a method as private, that means if you use my class, you're not supposed to call it. Because I might change its name, I might delete it completely, I can do anything I want to it. But if the method is public, so add, remove, list, and count, those are the API or the public interface of the class. So I guarantee that as long as the blit range index class exists, it's going to have an add, a remove, a list, and a count that will behave exactly in that way. So once you have a class with public methods, you're not supposed to change them because other people might depend on them and that will make people unhappy. Okay, so we said that these wires hold, we said that this range index holds wires, right? So if you have these wires here, they're not really numbers. I know how to compare numbers. I don't know how to compare wires. That's not something that's readily comparable, right? So we have to bridge the gap. We have to bridge the gap between numbers or things that are comparable and wires. So the way we do that is the key wire pair class. And if you look at the key wire pair class, it has, I will write it as key WP here. So it has a key and a wire, right? That's why it's a key wire pair. And if you look at the comparison methods, lines 11 through 26, but if you look at 11 through 13, pretty much everything else is the same, then comparisons are done in a certain way. So the first criterion is the key. So if you have two key wire pairs that have different keys, then the one with the bigger key wins. Now, if they have the same key, then this field called wire ID is used to break ties. Right? So first key and then wire ID. What's the wire ID set to? And where? Where would you set a field in a nice class? In the constructor. Very good. So where is it set? Line number? Line 10. Okay, so the wire ID uses the same object IDs that we had earlier. So each wire has a unique ID that's between 0 and the number of wires. Okay, so this works when I insert my wires into the index. What's the key for wires, by the way? Where are wires inserted into the index in the algorithm that we have, and what's the key? So the algorithm that we gave you. Yes? The, which one? I couldn't hear you well.
The y coordinate.
The y coordinate. Okay. Can you tell me which line? So the intuition is very good. You want the wires to be keyed by the y coordinate so that when you do a range query between this guy and this guy, you get these wires. So that's the intuition. Now, what's the code? Line, I didn't hear you well. I think you said that right. 13. Okay, so wires are added to the index when an event of type add is processed, right? Line 12 says if event type is add, so that's probably what we want, and line 13 adds it to the index and builds a key wire pair with the key, the y coordinate of the wire. Okay, now let's look back at the keys and see that we have two special key wire pair classes, key wire pair L and key wire pair H. These don't want a wire. Why would you think, why would I make a wire key pair that doesn't want a wire? Why is that useful?
You have the minimum and maximum wire IDs.
Okay, so very good observation. So the wire ID for the low key pair looks like minus infinity, and the one for the high key pair looks like plus infinity, as long as I don't have more than a billion wires. Okay, what do these things not have? They don't have a wire. So if you look at key wire pair L and H, if you look at the initializers on lines 2 and 8, they only take a key. They don't take a wire. So this is useful in which situation? Where do I want to create an index key that's not associated with a real wire?
When you want to make the list, when you want to do a query.
When I do a query. Okay, very good. So if I'm querying, if I have this vertical wire, which starts, say, from, what do I have here, from minus 80 to plus 80, then I would like to make a low key that corresponds to minus 80 and a high key that corresponds to plus 80. But I don't have any wire with a horizontal coordinate of 80. Right? A hackish solution would be to make fake wires with those coordinates. But if I make fake wires, God knows where my system is going to break elsewhere. So instead, a clean solution is to have these key wire pairs so that when I insert wires, I have a wire. And when I don't, the wire is set to none. And the wire IDs are these special values, minus infinity and plus infinity. So what's cool about setting the wire IDs to minus infinity and plus infinity?
So that if you have a wire at, like, if you call key wire pair L for 80, you have a wire ID, this wire ID is a negative infinity, so it's going to take that wire also, because this wire ID is less than the wire ID of the wire that could be there.
All right.
Just do like less than.
Yep, cool. So if I have a real key wire pair, and it has a wire whose coordinate is 80, this is going to be bigger than a key wire pair L with coordinate 80, and it's going to be smaller than a key wire pair H with coordinate 80. So if you do a query using this and this, it's going to grab all the wires with coordinate 80. Does this make sense? Okay, so what's cool about this in terms of coding? Do I have equal keys in my range index? Do I have to handle multiple keys with the same, like multiple equal keys?
Oh, actually, in this case, yes.
Do I?
Because if you have all the horizontal wires, then it's possible that you have two horizontal wires of the same.
Okay, so if I have two horizontal wires, say this guy here and this other guy here, this guy here, what's the key value pair for it, key wire pair? So say the coordinate is minus 95 and the wire ID is 2.
Oh,
The key wire pair is, the key is minus 95 and the wire ID is 2, right?
yeah.
And then for this other wire, suppose the wire ID is 10, the coordinate is going to be minus 95 and then the wire ID is going to be 10. So how are they going to compare?
Oh, then that one's less than that one.
Yep. So even though I have two wires with the same y coordinate, so the key as far as the algorithm is concerned is the same, in the implementation the keys are artificially different because I introduce an artificial ordering on the wires using that wire ID. So in which case would I have the same key inserted in my index twice? Yes.
So like visually, if the wires are on top of each other.
Okay, so if these two wires overlap, say this guy ends here and this guy ends here, and if I put their keys into the index, they're still different.
Only if they're the same wire ID would they have the same.
Okay, and when do two wires have the same wire ID?
If one of them was like,
Suffices, I suppose.
I was gonna say if one of them is negative infinity.
So no, let's assume that the infinities work the right way. Yes? No. Okay, so wire IDs are unique.
Right,
Every
everything
wire
has the
has its
same
own wire
wire.
IDs. Wires will never have the same wire ID. So the only case in which you have two equal keys in the index if you insert the same wire twice. Would you ever want to do that? Probably not. You're going to get the same wire twice from the range query, and that's not useful. So when implementing a data structure for the range index, we don't have to deal with equal keys, and that is nice because that's less thinking. Now, when we do a query, will the keys in the query be in the range index?
Not necessarily.
So when we do a query, how would I do a query? If I want to do a query from minus 80 to plus 80.
You grab all the horizontal wires whose y coordinates are between.
So you're thinking in the range index. I'm thinking as a client of the range index. So you have this range index class. How would you issue a query to the range index?
List from L to H.
Okay, so I would call the list method. And oh, crap. I thought I'm going to avoid doing that today. So L and H are keys, right? How do I construct my keys?
Oh, use y parallel.
Okay, key wire pair left of 80. Low and key wire pair high of 80. Right, so then I'm going to get these. I don't have wires for this 80 coordinate. Sorry, minus 80 to 80, because that's what the query looks like. So I don't have wires for these coordinates. So I'm going to use these special values. And this one is smaller than all the wires with coordinate minus 80. This one is bigger than all the wires with coordinate 80. Will these keys ever be in the index? Nope, we're only using them for updates. If you put this in the index, then when you're getting it back and you try to get the wire associated with it, you're going to get none. Your code is going to crash. So if I have a query, will the keys in the query ever be in the index? No. So that means fewer border cases to consider when implementing query. So all the keys in the range index are different, and the keys in the query will never be in the range index.
Oh, so when you do the count, you know that L and H aren't in your range index.
Yep.
You have to count for that.
Yeah, so in this case, that's why the code didn't fail any test. Because I'm not using numbers, I'm actually using this. So for the number analogy, this is equivalent of when I'm doing count of 411, that would get rewritten as count of 399 and 11.01, and this works. So this is what these two values are doing. Except if you try to do 0.99 and 0.01, that's brittle because you might actually have those keys. All right, does this make sense? Any questions on this part? Nope. Yes. Yes.
So is this taking into account that situation where you have a gap in the wires, but you still have a Y value associated and it's going to it?
Sorry, say that again?
That example right there?
Yeah.
Like,
Oh, so are you worried about the fact that I'll have two equal keys, or are you worried about the fact that these wires are crossing?
no, that they're not overlapping. So you have a wire, and you have a wire coming down, and you have another wire.
Okay. This is not going to account for that. You have to write a better sweep line algorithm.
Oh, okay.
This, what I'm talking about now, will make your range index faster. Or it makes your range index simpler to implement.
Okay.
So this is magic behind the scenes that makes your code smaller. You still have to implement a sweep line algorithm that makes sure that when you have a range query, it would either return less false positives or ideally no false positives. And then the code would be faster. But then when you do that, you'll see that it's still slow because the range index that we have here isn't optimal. Why isn't the range index here optimal, by the way? What can I improve about it?
Add and remove.
Add and remove, okay. So we're using the comparison model because it's convenient to use the comparison model. You have complex objects, you implement those 6 methods that you see in keywire pair, and bam. You can do comparisons, you can use any data structure and algorithm that assume a comparison model. What's the penalty of the comparison model? What's the problem with it? Yes?
It'll never be slower than, or never be faster than log n.
Yep, so if I want to do a sort, that is n log n. And if I want to do a search, that is theta of what? Okay, now what are the best bounds that we have for these if we can go outside the comparison model? Just to see if you guys are paying attention in lecture. So best running time for sort if we don't have to use the comparison model. N. Okay. Best running time for search if we don't have to use the comparison model. Order 1 with hashing. Can you do any better than that? Okay, so sort has to output an array of n elements, so it can't be faster than order n. Search has to output yes or no, so it has to output something, so it has to be order 1. So this is as fast as it gets. We're definitely not going to go faster than that. So we have this extra log n factor that we pay if we use the comparison model, if we don't collect more information about our keys. But in return, we have the convenience that all we have to do is establish an ordering relationship. Okay, does it make sense? Cool. Let's try to talk about the list pseudocode, which you might have seen on the pset before. And that's on the last page here. So I can't give you a proof of why it works, but we can work together to figure out how it works, get an intuitive understanding. So let's get the keys here, and let's assume we're using a regular BST for implementing a range index. So I'm going to put my keys in a BST. 8, 3, 2, 5. Okay, so list does 2 things, LCA and no list. Right? What's LCA? So suppose I want to list all the keys between 1 and 6. First, I'm going to call LCA and get some answer, and then I'm going to call node list. What's the answer for LCA?
3.
Okay.
The node at 3 with key value 3.
Sweet. LCA. What is this? What's LCA? It's okay to give out an answer to a dumb question on the pset. So LCA is lowest common ancestor. Very good. It's the lowest common ancestor of what?
The subtree of
values that should be returned by node list.
So usually you have two nodes in a tree and you want to return the LCA. So if I want to find out the LCA of 2 and 5, that is 3. If I want to find out the LCA of 2 and 13, that's 8. Now if the keys are not in the tree, what does the LCA give me? It's where they would be if they were inserted, right? So 1 would be inserted here, and 6 would be inserted here. And then their LCA is indeed 3. So what does that tell me? Why is that useful?
You can cut off a bunch of the rest of the tree, so you don't have to look at them.
Okay.
See if
A
they're
bunch of or the rest of the tree?
Right, the rest of the tree.
The rest of the tree. So if 1 is here and 6 is here, then I know that all the keys, so 3 is to the left of 8, so all the keys to the right of 8 are going to be bigger than 6, for example, right? Because 6 is here and it's under 8. So I can throw this away. Now if this would be to the left of something else, because 1 is here, I know that all the keys to the left side of that thing would be smaller than 1. So this subtree has to have all the keys between 1 and 6. Yes?
You don't include 8, right? Where do you remove 8?
Yep, so we only look at the subtree rooted at LCA. So LCA is passed as an argument to node list. And node list seems to do sort of this is a pre-order traversal. So you look at the key, you look at the left node, at the left subtree, you look at the right subtree. Except there is some magic there, and in some cases it doesn't go and look. Let's see, what would a good case where it doesn't go and look like? Let's get the same tree. Suppose I want to do a list between 4 and 11. Sorry, between 4 and 10. What's the LCA of 4 and 10? 8. Okay, so node list would have to start here. Suppose I'm here and I go to 3. I know 3 is smaller than 4. Do I want to go left? Everything to the left of 3 is smaller than 4. So this entire subtree can be pruned. Now suppose I'm on the right side and I'm at 11. 11 is bigger than 10. Do I want to go right? So if 11 is bigger than 10, I never want to go right because everything to the right of that is bigger. Okay. So this is how pruning works. Now, if I'm at 3, can I stop? I can't stop and exit completely because on the right side of 3, I might have keys that are bigger than 3 and that are in my interval. And in this example, that seems to be the case. Okay, let's look very quickly at an intuitive way of analyzing the running time for this. So suppose I have my LCA up here, and suppose I go on a path from LCA to L, and then let's not worry about about H. H is somewhere here. The case is going to be symmetric. When I go down the path, after I go here, would I ever want to go left? So if this node is before a right turn, then I know that L is going to be bigger than that node. Right? So I'm never going to take a left turn. Like this subtree will be pruned, this subtree will be pruned, this subtree will be pruned. Now, if I go right here, what happens? All the nodes here are going to be between L and LCA. LCA is smaller or equal to H, so all these nodes here are guaranteed to be nodes that come out in my list. All right, why am I doing this? So I was saying before that I absolutely have to have an order I because I have to produce the output list. So if we look at lines 3 and 4, line 4 outputs a key, right? So line 4 is definitely order I. And line 3 is an if condition, so we know for sure that line 4 is only going to execute 4 keys that are between L and H. So this algorithm is going to visit some nodes in the tree. For example, if I have a list of 4 and 10, it's going to visit 8, it's going to visit 3, 5, and 11. And for some of the nodes that are visited, it's going to output them. Right? This guy gets output, and this guy gets output. The nodes that are output are order I. So those are already covered in the I term. And in order to get the running time, what I need to know is how many nodes do I visit that are not part of the output? Because if I end up visiting the entire tree, then that's order n plus I, so order n. But if I only end up visiting a few nodes outside of the output, then that might be a lot better. And here I'm trying to argue that I will only visit a few nodes outside the path. In fact, for every node, I'm going to visit at most the node and the node at its left. And then everything to the right of the path is between L and H, so everything to the right is going to be output. So everything here is in order I, and everything here is visited and not output. And potentially everything on the path as well. So what's the height of a path in a binary search tree? Regular binary search tree. Okay, n worst case. So worst case, the height is order n. But we usually call it height because on average, at least, it's log n. So it's somewhere between n and log n. What is the running time for list in a binary search tree? If you buy this argument here, what is the running time? Okay, so you could say n plus I, and you're perfectly correct. But we can make it a bit better. So what's the height of this path? H. So what's the running time? Okay, cool. Does this make sense at all? Is this too complicated?
That's the running time for what?
So this is the running time for list. All right, so questions? Is this too far out? Did I lose you guys completely?
Wait, so it's
Makes
order-
perfect sense. Okay, I like that.
It's order n plus I because you could go down a path that could have up to n nodes on it, right?
Yep.
And then it's order I because you have to add that many elements anyway.
Yeah.
But better case, it's log n. I mean, no, it's order h.
So I'm saying that it's a binary
Yeah.
search tree of height h.
Height
And if
h, oh.
h is better than n, then I'm going to do much better than n. So that's why I'm putting that h there.
I think it's just a little confusing on that part, but the checks
Yes.
make sense because, of course, if that's a smaller node, you're not going to look at the left, and of course you're going to look at the right. That's bigger than your smallest element, right? Or, so if you go to the right, that means that.
So here I know that L is on the left, right?
Uh-huh.
So L is smaller than this key.
Mhm.
Everything to the right of this key
Mhm.
is between L and LCA.
Yeah.
LCA is smaller or equal to H. So everything here is between L and H.
Mhm.
So all the nodes here are going to be output. So all the nodes here count as I.
Okay.
Now when I turn left here, this is going to be smaller. This is smaller than, sorry, I keep saying this. Smaller than L. So this is smaller than L because L is on the right. So this thing is going to be pruned. So I will visit the parent, this node, and that's it. I'm not going to look down. And this is how the nodes look like. Everything that's to the left of the path is not visited. Everything that's to the right is output. Okay, any more questions? Okay, I hope you get it right on the PISA then. All right, thanks guys.
Wait, so after we
So 60 is a conservative estimate for a really old laptop. Okay, that's the baseline.